Now, if you were a sound wave at a typical air temperature and you went around the Earth, it would take you 1 day. That's still pretty slow. Guess how long it takes a light wave to go around the Earth at this incredible speed.
Maybe a couple minutes.
I was going to say 13 seconds, but it's not. It's 0.13 seconds. Light is incredibly fast. It is incredible. I just wanted to give you that picture so you can see the difference between light and sound. It's just incredibly fast. All right. All right, we're going to change gears and cover another topic today. And I need to introduce it and tell you its name in a second. Let me get rid of this. Anyone need this board work? Which one? You need both of them?
I'm
Almost.
You can look at mine.
okay, I think I have it.
Okay.
Yeah.
I'll just take this half then. This is fine. Alright. We have to remember back when we were younger and we were playing with airplanes. There probably is a moment that you were playing with an airplane, be it be metal or paper or whatever. So everybody, can you give me like an airplane finger? Like this maybe, or whatever. You can make it like this if you can't copy this. Alright, so take your airplane out, and now I want you to fly your airplane a little bit. And now I'd like you to add sound. What's your airplane? Well, what we're studying today, it's kind of interesting. I didn't hear one person, I didn't hear a lot of participants, but I didn't hear everyone going, you were all going, yeah. And what we're studying today is something you knew intuitively, probably when you were 2 years old, but you didn't know its name, and it is the Doppler effect.
So.
Yeah. I think it's loud. Okay.
Aaron was obsessed with
This is
that.
how we did this a couple years ago.
Oh.
Yeah.
And didn't we like wait outside until we heard an ambulance pass?
Yep.
That's a good idea.
Remember that? That's how it gets like the pitch changes.
Yeah, that's right.
It gets closer.
So everyone's had the experience where you've been at the train or near the train crossing and the sound goes, no. So it went from high pitch to low pitch, and we're going to study why that is and actually be able to calculate the frequencies according to this effect, and it's called Doppler effect. It's very important when we go into outer space. We're not looking at sound, but light also has a Doppler effect, but it shifts its color. So we can tell how far an object is away by the Doppler shift in its color. So we're not going to do that. That's a lot more complex. But we're going to do it with sound on good old Earth, and you'll have the principle that applies in outer space as well. So, all right, well, we already learned that pitch is related to something. So this is a pitch change, and it's related to what part of the sound wave? Do you recall we discussed it earlier? Was it amplitude or frequency that pitch is related to? It depends.
Frequency.
On what? Frequency, right. So if you recall, the word frequency, like here's a good old lazy sound wave. Actually, we don't draw them like that. They're actually clumpings. But here's a good old wave, and here it has a certain frequency. Say here's a human ear right there. And so they are hitting that ear at a certain number of crests or troughs, crests per second. But if it was like this, I'm trying to draw another one this is supposed to have the same amplitude, but a different frequency. Now more crests are going to hit the ear at a second. So the pitch will be higher. So we talked about that already. So now I'm going to take, say, a car, because we're going to mess with the car. I wonder if it would work outside if we stood and I just drove by you and honked the horn, because I'd make everyone mad. I wonder if I could do it in the parking lot. Is the parking lot long enough?
Probably.
All right.
Or you could just go on the corner if we don't sit on the corner.
Yeah.
All right. Here's a
And then turn around and come back.
here's a car. Graduated from my smart car here. So we have the horn is being beeped, and from it comes out a frequency like that. If the car is still and you, who are outside of the car, are still, if they're both still, the horn would sound one pitch. Go, ee. It wouldn't go up or down in pitch. So if you are still and the car is still and the horn is blown, there'd be no Doppler effect, no pitch change. But in real life, usually one or both of these are moving, and that's what we're going to be able to figure out the pitch change when we finish this discussion. So this time, I'm going to draw a car, and I'm going to draw the waves more realistically, because remember how they're not really like this. This helps when I'm talking about frequency, but they're really in clumps, right? So I'm going to draw like rings like this, because that's how sound waves actually look. They come out in these big rings. So there's the horn sounding, and there's the clumping, the crests and the troughs from the horn blowing. Let's say that you are standing over here, and the car is going to start moving. Right now,
Oh gosh.
you're not in the way. See, the road goes in front of you. All right, don't want you to stress out. All right, see if I can picture this. As the car, this time, you're standing here, still, you're still. This time, the car that is beeping is moving. So we have a beeping mover. So we have, this time, here's the first sound wave that the car emits. But the car is moving. So as the car moves, it's going to move into and catch up to that sound wave, so that when the next one comes out, it's going to be crowded like that. And then as the next one, as the car keeps moving, it's catching up with those sound waves that it's already emitted. And they start clumping together like that. Does that make sense? As the car moves, see, here's what it would look like if the car wasn't moving. But as it moves and more sound comes out of the horn, they are going to crowd together in a way that is unlike it when they're both still. So now we have a higher frequency, so the pitch goes up. The pitch goes up as the frequency goes up. Because of the moving car, we end up with that happening. So when these get to your ear, they're all clumped together, the frequency is high, and the pitch gets high. What happens when the car goes past you? So there you are, the frequency is high and the pitch is high, but look what happens on this side of the story. Here is the car, and it's moving still in this direction, and you are still. So now it's still beeping. Its horn is totally stuck. So as it goes this way, it's still catching up and clumping those sound waves as it rides into its own sound waves. But look what you're going to hear this time. Now, when it goes past you, the sound waves, the frequency is way lower than it should be. And the frequency goes down, the pitch goes down. So that's why it goes like that. where you would think the frequency would stay the same all the time, but it's this motion that changes things. All right. So as the car heads toward you, the frequency goes up, the pitch goes up. As the car goes away from you, the pitch goes down and the frequency goes down. So